Hi everyone. So today the first one to present is Wilson. You wanna get started?
Yeah, absolutely. Let me share my desktop and we'll get started. Okay, can everyone see my screen?
Yes.
Great. Okay, well, hey everyone, my name is Wilson. I am a part-time graduate student at Georgia Tech, and today I will be discussing about extending FairLearn to include RL bias analysis using VW. This past summer, I was mentored by Rodrigo. In order to set up the structure of the presentation, I'd like to start off by shaping the motivation of the problem. Then what I'd like to do is address some of the partial results that were unpacked and uncovered this summer. And then lastly, address some takeaways and next steps to motivate further study. So traditionally, in a full information setting, we can use any supervised learning framework to sort of predict the, we're going to build a use case around graduate admissions throughout this entire presentation. But basically what we'd like to do is essentially predict the likeliness of an applicant receiving admission to the university. And this can be done through any supervised learning framework. Any classification supervised learning framework. X would represent the set of contexts, the set of features that represents each of the applicants, and Y would represent the decisions made by the admissions committee. But the questions that we do run across when we're looking into this is this model necessarily fair, and what does fairness even represent in this case? So in order to understand the notion of fairness, we need to introduce sensitive features, which is a subset of the set of features that represents attributes distinguishing the subpopulations of X. So in the use case for graduate admissions, that would be either gender or race. So currently, FairLearn supports a lot of the implementation of the reduction algorithms in the supervised learning framework, where they impose fairness constraints for classification problems and some state-of-the-art approaches like exponentiated gradient and grid search. But under the assumption of the full information setting, we don't necessarily capture the reality of what graduate admissions go through. Specifically, we don't necessarily know if the decision that we're making for an applicant is correct or not. So how do we address this full information assumption? By relieving that to the partial information setting, we introduce, I want to distinguish the difference between what a counterfactual outcome is and a factual outcome is. So factual outcomes are essentially the decisions that are made by the learner, and counterfactual outcomes are the unknown outcomes that are hidden behind the setting, the construction of the setting. VW supports a wide suite of exploration strategies, including explore first and epsilon greedy. And we use these exploration strategies to essentially have the learner decide which outcome would be chosen for a specific application when introduced into the contextual Bandits setting. Continuing with the building of the contextual Bandits framework, we also look into using observed rewards, and we look into the associated propensities of taking various actions. And in order for us to define these rewards and propensities, we need to define a cost function that will allow us to have the learner observe the rewards so that we can create an optimal policy after multiple iterations. But the question still remains, is this policy that we're learning and introducing in this contextual Bandits necessarily fair? We can actually approach this in two different approaches. So this specifically, is online learning a good way to really measure the fairness of these policies? Should we continually observe these rewards in this setting? Because that could potentially influence some fairness-related harms in our system unknowingly. And secondly, what parts of the contextual Bandits would influence the fairness-related harms in our overall system? So our goal this project is sort of twofold in the sense that we're trying to identify specific parts of the contextual bandits that would influence this introduction of fairness and unfairness inside our system, and how can we better assess fairness in an offline learning framework. Going on that approach, we introduced counterfactual learning and contextual bandits, where the goal is essentially trying to, instead of learning policies iteratively for every observation in the contextual bandits framework, we generate log data, which would be a finite set of data points where we run some logging policy pi-not. This pi-not is applied to the graduate admissions use case. This pi-not would represent something like the standards that the admissions committee already had previously set for the previous semester. So we want to generate these log data, and with this log data, we can do two things with it. We can evaluate fairness on this log data, and we can also look at it from an offline setting where we can estimate average rewards of evaluation policies, and hopefully we can do the same thing for other fairness metrics offline. So going to our partial results this summer, we used a synthetic graduate admissions data set. Specifically, in these two plots here, we performed 30 different simulations of the log data generation process with the fixed logged policy using the explore first strategy. So on the left, in the plots, on the dashed lines in the left represents the exploration phase, and the right would represent the exploitation phase. And then we evaluate fairness metrics using a 95% confidence interval to study and see the fairness here. So in both plots here for the criterion of selection rate and false positive rate, so we observe that there is a male bias in the exploitation phase. Specifically, selection rate represents the likeliness of a male applicant receiving acceptance, and the false positive rate indicates that the probability of a male applicant receiving acceptance, given that that male applicant does not deserve acceptance to the university. We started introducing two additional fairness criterions as well. Demographic parity basically defines fairness by setting the admissions rate for female applicants and male applicants equal to each other. So it tests how equal are these two admission rates are. And equalized odds is an extension of that, where instead of looking at these the admissions rate of each gender, or of the entire gender group comparatively together, we look at them individually and study how likely would a male applicant who receives acceptance is equally likely to not receive acceptance, given that they deserve acceptance. So we define that as equal opportunity. And in both cases here, we observe that the two plots here, the equalized odds ratio is less than the demographics parity ratio. In practice, this equalized odds ratio is a better indicator of how fair our model performs, and our demographic parity ratios is more of an indication of how biased our data set is. So we see that there's more of a bias in the contextual bandits framework. And lastly here, what we did was we also additionally created an evaluation policy that is intentionally designed to be unfair by making white male applicants more willing or more likely to be accepted. We use average rewards to study the impacts of how the training process behaves, or how the learning process behaves. And we observe that average rewards gets inflated for this evaluation policy. In the faint line shows the online evaluation of that evaluation policy, and then the dark line here represents the IPS estimation. And we see that they're correctly inflated because based off of the construction of our evaluation policy, the learner receives more rewards for accepting more male applicants. So they continually accepts more male applicants here. So to summarize the partial results that were uncovered this summer, we see that exploitations of contextual bandits can potentially yield unfair results. We also would like to establish that estimators in the contextual bandit settings would be a good first stepping stone to devising offline fairness metrics in contextual bandits. Some takeaways that I've learned this summer was mainly learning a ton of new topics, including causal inference, contextual bandits, and AI fairness. And some additional takeaways that I've learned is that managing a full-time work alongside with my studies has been quite challenging for the summer. But yeah, I'm happy to have all these partial results this past summer. Some next steps that I'd like to take in continuing with this analysis and the contributions to both BW and FairLearn is to continually be engaged with the communities and see how much work we can continue with this progress. So lastly, I'd like to thank my mentor, Rodrigo, for all of his support and the FairLearn community for introducing me to the community and being involved with their efforts. It was a very great summer semester. I really enjoyed the experience. So thank you so much for the great experience. Any questions?
So I have a question, which is just how easy is it for other people to kind of follow on? How available is the code that you did in the testing framework?
So the code is currently structured a little messily, so it's not the easiest, but what I can do is sort of structure it in a more readable format so that it's accessible to all readers.
That sounds pretty desirable.
Mm-hmm.
All right, thanks, Wilson. Our next student is Varun with AutoML.
Hi, everyone. I'm working on the AutoML style algorithms for online contextual bandits, and I worked with Paul, Olga, Chi, and Cheung over the summer. Really appreciate their support for the work. Online learning in general requires careful tuning of hyperparameters. Hyperparameters can be anything: featureization choices, learning rate, regularization parameter. In this work, we focus on featureization choices. But in general, online learning is challenging, and most of the tuning which is done currently, it is done manually. So by using AutoML style algorithms, one can alleviate the need to manually tune all these hyperparameters. So online learning presents unique challenges in terms of the computational constraints we have on real world systems. The amount of data that arrives is not fixed, and there's no natural point for stopping. At a given iteration, the algorithm doesn't know when the data is going to stop coming, so we don't know. There is really no natural point for stopping. So the question arises here is that how do we adopt a good choice of configuration or feature choices? Now, we focus on the feature choices in this work, but in general, it can be any parameter, regularization, learning rate, or any hyperparameter can be, which can control the performance of the algorithm. This problem has been studied, AutoML style algorithms for online learning previously in a full information setting. And this is the work which came recently and was published in ICML Chacha for online AutoML. Our focus in this work is on partial information setting. So let me go ahead and touch a bit on the full information and partial information setting. Like the name mentioned, in full information set, in an online learning problem, in general, we have an input at iteration t, and the environment has an input. The input goes to the system, the learning agent, and we make a prediction on that input. Now we get the prediction output yt, and then environment reveals the feedback to the learning agent, and based on that, learning agent updates its models. So in a full information setting, learning agent maintains few models, and each model gets to receive the feedback, which is not the case in bandit or partial information setting. Only a few models get to receive the feedback. So bandit setting is challenging in the sense that the data which in full information setting, all the models have access to more data, more feedback, more data, which is not the case in Bandit setting. We focus on the featureization choices in this work, but again, learning agent has hyperparameters and we can work around with any hyperparameter. And to update the models, we use loss bounds using importance weights, which I'll go in a more detail a little bit later. And as a metric to see the performance of the algorithm, we use progressive validation loss. So the algorithm which we come up with in the partial information setting, we call ChaCha-CB. It successively chooses the configurations, feature interaction choices in our case, online at a given input xt to predict the label. Currently, we are using CB Explore and CB as our policies. And we update the loss bounds. Loss bounds are basically the ranking metric to decide which model are we going to select at a given iteration to make the decision. So among the models I showed in the figure, there were 4 models. So loss bounds are basically the way to measure which model we'll select. And we use importance weight to update the loss bounds only for the policy which predicted the same action that was played at a given iteration. So this is the crucial difference. In full information setting, we'll update the bounds for each model, but in Bandit setting, in the partial information setting, only the models which predicted the same action will get to receive the feedback. In terms of the workflow over the summer, I spent a initial few weeks into becoming more familiar with the problem and work around the full information setting, ChaCha code, and just reading the paper and exploring the code in the beginning. And then I studied COBA, which is a benchmarking framework built specifically for contextual bandit research. And it has several benchmark algorithms. And the motivation was, once we have our system working, we can easily benchmark our algorithm with already existing in COBA, and then compare with some of the baselines on various data sets from OpenML. Speaking of baselines, this research line is pretty new, and there are not many baselines in the literature. So I used baselines which were there in the ChaCha paper. The one is exhaustive, where we try all the pairwise interactions. Basically, let's say we have n namespaces in the beginning. So n choose 2 will be the total number of interactions. So exhaustive basically tries all these configurations. Vanilla, where we don't have any interaction configuration and just run the algorithm without any interaction. In random, we pick a few random configurations from the exhaustive configurations and then use them all the time. So basically, let's say if we have A, B, C as the namespaces in the beginning, exhaustive will, so total number of configurations will be A, B, B, C, A, C, and A, B, C is included in everything. Exhaustive will work with all these 3 configurations. Vanilla will work with A, B, C only, and random, let's say we decide to work with 2 random models, 2 random live models, then it will pick 2 configurations randomly from here. So these are the baselines. One of the sanity check. So in ChaCha, basically the intuition is that eventually the ChaCha-CB will be able to pick out the good configurations as the algorithm proceeds. But to make sure that will there be any good configurations in comparison to vanilla, we did a sanity check where we compared the performance of exhaustive. Exhaustive is basically all the configurations, vanilla, all the interactions, vanilla, no interaction. So in this case, we are plotting the progressive validation loss, and lower is better. So we see that exhaustive is performing better. So certainly there are some configurations which are interaction configurations which are better than no interactions. So in this case, we can hope that ChaCha-CB will be able to pick out those configurations as the algorithm goes on. And so for this data set, we can hope that ChaCha-CB will be able to outperform, will be able to find the configurations which are good in terms of progressive validation loss. So with vanilla, we compare ChaCha-CB, and this is the greedy policy we are running, completely greedy. And these are the results for 4 different seeds. In all the configurations, ChaCha-CB performs better than vanilla. Lower is better here again, progressive validation loss we are plotting. With random, Sometimes ChaCha-CV performs better, and sometimes random. So maybe random gets lucky sometimes to pick the to randomly pick the configurations which are good. So if it ends up picking those, then it performs better than ChaCha. And actually, this is the line of work we will be investigating in future by allowing ChaCha to go further over the just pairwise interactions. That will be worth diving into if if there is any difference in the performance ChaCha, because random only picks random configurations from pairwise interactions. And in this case, we have restricted ChaCha to pairwise interactions, but we can allow ChaCha to go to higher order interactions as well. In terms of the current work, currently we are working on making sure that ChaCha-CB actually sticks to the best configuration eventually, which it should in theory. For that, we are running CB separately on all possible combination of configurations. So let's say if we have 2 namespaces in the beginning, so just run these configurations separately and see which one is better, and then make sure that ChaCha-CB is able to find that configuration. And then later validate the confidence interval logic we have implemented so far. So actually, we did the manual testing with 3 namespaces. And so there will be total 8 possible configurations, and we plotted their mean progressive validation loss. This is the mean over 25 runs and the standard deviation. So it seems that AB is better than AC. So we would hope that ChaCha-CB will be able to pick out AB before AC in the beginning, and eventually it should stick to probably AB plus BC. But this is something we are testing right now. In terms of the further plans, we want to make sure that CB model correctly runs in the ChaCha. Currently, probably there is a bug in the code and it's not acting the way we would want it. We expect it to, and then integrate it with COBA and test on different data sets with COBA. COBA has several data sets out there. In terms of learning outcomes, I learned during the summer, to say the least, that I would say print statements won't get you far when it comes to debugging the code of a huge scale as ChaCha. And I never used a debugger before, so I realized the importance of a debugger. And code management, object-oriented programming, the code was so big, and maintaining class and everything, managing the code is a crucial skill. I think I'm going to appreciate more going down the future, and breaking down a bigger problem of this scale as online learning, and figure out the pieces of code individually by breaking them into sub-problems. It was definitely worth, I should have paid attention to. And in terms of general skills, I had a full-time internship, so managing time was really crucial, and setting achievable project goals during the entire project, and also communication skills, just to collaborate with my peers and collaborators, and communicating your ideas effectively so that I didn't have to say the same thing 100 times. Is something I will appreciate more moving forward from here. So that's all for my project. I'm happy to take any questions here, but really appreciate, and thanks Chi, Olga, Paul, and Cheung for a wonderful and productive summer.
Thanks for the presentation. Do you have any questions? All right. In that case, thank you again. And our next presentation is Muhammad with Tensorboard and Tensorwatch.
Can you hear me?
Yes. Ooh, okay. Yeah, we can see your screen now.
Okay, I cannot share my video. Okay. Oh, I cannot share my video. Would that be a problem?
We can see your screen, so you're just sharing your desktop.
Oh, okay.
So we should be able to see your presentation.
Okay. So my name is Ammar Abid, and mentor. I'm one of the students in this RLOS 2021, and my project this summer is Tensorboard and Tensorwatch integration, which is mentored by Mr. Jacob Elbow. So let's get started. So first, I would tell a little bit about myself. As I just told my name, so I'm from the city Peshawar in Pakistan. I'm a junior, third year in doing my bachelor's in computer science from FAST Places here in Pakistan. And one of my hobbies is that I like to gain beneficial knowledge. I like to do stuff that I'm curious about. So first, I would like to give a little bit motivation about visualization, like why is it necessary. So when you do daily to daily machine learning experiments, it becomes quite hard to understand machine learning results. Like you see all of these metrics and this and that. So visualization helps you in that problem, and it's necessary to understand patterns. It helps you to dig out patterns. Visualization gives you a good insight, like how is your model performing, is it performing well, or is it performing really bad. Yeah, it can also give you insight that is it overfitting, underfitting, etc. So yeah, so it also allows you to understand the data just by giving a look, because currently human brain can process images 60,000 times faster than text. And trust me on that one, because I just found that on a blog. So yeah. So first I started with integrating with Tensorboard in the start of the summer program. So what is Tensorboard? Tensorboard is basically a visualization and a tool for machine learning, which gives you basically visualization in many paradigms, and it also has some other capabilities too. So yeah, so progress in on that in the month of I think May was that I created a df2vw22 Tensorboard class, and yeah, I did all of the work in Python. So yeah, please keep that in mind. So yeah, so I did all of this work in Python, and I created this class in I think in month of May. And what this class does is that it handles the data frame and learn on that, and it utilizes some df2vw class which is already made. So yeah, I also created a VW22 TensorBoard class. What this class does is that it handles writing of logs of metrics for TensorBoard. And I modified the vw.learn to provide logs for TensorBoard. So now anybody using vw.learn can use this class as a callback and can basically log the metrics. Right now, the metrics supported are average loss and since last. So yeah, let's discuss a technical problem. Basically, basic metrics of PW are average loss, since last, prediction, label, num features. So plotting label and prediction as line plot would not make sense, right? Because it does not suit to plot it as a line plot. So the more suitable plot is bar plot. But currently, TensorBoard does not support bar plots. So that was one of the reasons that I did not do that. So yeah, so let's move forward, and I would give a little bit introduction about PW reductions. So many machine learning problems can efficiently be reduced to small solved problems. So how does this help us? This allows you to frame learning problems effectively and achieve the best solution. This is also called reduction stack. If you don't know about VW reductions, you can read more about it in its documentation. Okay. So the progress on that, which I did before my second check-in, was that the VW22 TensorBoard now can draw graph of VW reductions. So basically, it draws a graph of VW model. So, and it can also now write VW initialization arguments as text. So yeah. So technical problem. So basically, the so basically TensorBoard works is that it needs a log file, right? It reads from that log file, and that log file is basically it's an event file. And so for writing that event file, we are using a library TensorBoard X. And TensorBoard X, it's an open source library. So basically TensorBoard X did not had any support for writing a custom graph. So Yeah, because of that, I had to understand some of Tensorboard X source code, and my head was usually spinning around that. But with the help of my mentor, we got around to the main points, and uh, I was able to figure out that how to make a custom graph. So yeah, excuse me. So there was a bug in Tensorboard X event writing. The bug was that what I was doing that I was creating a graph with the help of Tensorboard X source code, and I was creating an event out of it and logging that and writing that event to the event file, which would be used by Tensorboard then. So the problem was that the graph was not writing out, and I was not able to see the graph in Tensorboard. So yeah, basically, and the solution we figured out was that basically that Tensorboard X should just flush out all of the events in the event file after 30 seconds. So that's how we solved that problem. So I will give a little bit demo on that. There you go. So this is my Jupyter notebook, and this is in the examples folder in Python of Opel Rabbit. Yeah, you can check it out. Okay, so I'm here just importing the necessary stuff, and I'm using the iris dataset. Iris dataset, I'm using it as a reading it as a pandas data frame. Here, just seeing the columns, just converting the integer categorical columns to integers. Okay, so here I'm creating a df2vw object, as you can see. Okay, here I'm creating a VW object, and I'm using one agent for all, which is a multi-classification algorithm. And we have three classes, and dash p is for progressive output, and one is for progressive output for each line. So here I'm creating a VW22 Tensorboard class, and I'm specifying the logs directly that it should create an event file in the current directory under the logs folder. So okay, yeah, and later I changed the name of the df2vw to Tensorboard class to df2vw to tb or tw, and tw stands for Tensorwatch. So yeah, so I'm just passing the class vw to Tensorboard as a callback, and yeah, so basically what this fit method does is that it learns all of the data frame. Okay, and I'm passing the examples to it too. So basically what it does that it learns all of the examples, and it writes logs for TensorFlow. And I'm also calling the draw reductions graph and show args test too, because I also want to see the reduction graph and arguments as text. So yeah, so after you do that, first you would need to run this command tensorboard dash log div and specify where is the logs file, where is the logs folder. So yeah, and after that, whatever it prompts you, just go to that link. So yeah, as you can see, it's plotting the average loss for me, which is one of the metrics. It's also plotting the since last, and I can visualize it. So if you can see this cute little graph, uh, this is the reduction stack, gradient descent, scorer, and then OAA. Okay, you can zoom it to just okay, and you can see the text here. This benefits is that the benefit of this is that VW also sometimes take it also initializes some other arguments. Excuse me. Okay, so let's continue. So yeah, so the next step after the second check-in we took was that me and my mentor decided that we should move towards C++ native code, because that would be more beneficial for command line users. But for that I had to understand C++ native code, but being too much inexperienced with C++, I was also using a debugger, VS Code debugger, for first time. So I was facing problems, and I spent too much time on that. So then after that, I decided that I should just move towards TensorWatch and continue. Yeah. So TensorWatch. So what is TensorWatch? It's also a visualization tool. Basically, it's a debugging and visualization tool designed for deep learning, data science, reinforcement learning to visualize the results, and it's an open source project from Microsoft Research. You can use it in Jupyter Notebook to show real-time visualizations of your machine learning training, and you can perform several other analysis tasks for your models and data. You can also use it to provide custom visualizations, and I think that's one of the most strong points of Tensorwatch, that I was able to use it. I was able to integrate it more effectively because I faced less problems. So progress on that is that I created a VW to Tensorwatch streamer class. What this class does is that this class basically calls on the this call this class open the stream, and it's open the stream and basically a TCP/IP socket, and sends the values of average loss and since last while you are using vw.learn, or so basically it just sends those values to the stream. And I also created a VW to TensorWatch client class. Basically, you can use this class to as a client to see the plots, and you can create many clients. Streamer can be in one process, the client can be in another process, and that's one of the features of TensorWatch. And I also modified vw.learn in Python too. So basically, anybody using vw.learn can now use TensorWatch to see the metrics. And I also changed the name of df2ew to Tensorboard to df2ew to Tensorboard or Tensorboard. That means that this class now also provides support for Tensorboard. So you can also use this to visualize the results of the data frame in Tensorwatch. Okay. The problems.
We're running out of time.
Oh, okay.
Sorry.
Okay. So the problems and remaining work, once initialized, the port would be in constant use. So I dealt with that in the destructor, and the client should be running first, because if you don't run the client first, you would get problem. And bar plot work and reduction graphs remain. Yeah. So here's my takeaways and my experience. I got to work with one of the engineers at MSR Lab. One-to-one mentorship, and one-to-one mentorship was great because I'm one of the curious minds and I had many questions. Yeah, I learned more about the benefits of visualization. I learned Tensorboard and Tensorwatch because I had not worked in those before. And I learned more from experimentation and less from documentation, because Tensorboard did not have a documentation for creating custom logs and stuff like that. I also learned using VS Code Debugger, and this is first time in open source. So yeah, it was a great experience, and I'm really grateful for all of this. This was really one of the best experience. And I also managed my time with my semester, because basically my semester just ended in July due to COVID. So yeah, and I also got to utilize my time well. And one of the skills that I learned was that I learned to communicate, and basically learned to communicate my progress, problems, stuff like that. And one of the most important things that I learned is that I learned to take feedback. And I think that's one of the things that we students lack. Like, we like taking feedback. So I think that's great. And thanks for listening. And that's it from my side. Thank you.
Thank you, Maughan. Do you have any questions for you for the project? I found it to be really interesting. I think this could be a really cool thing to have, especially the Tensorwatch thing, where you can actually see progress live. It's really compelling. So our next student is Krystal.
Hello.
Thank you.
And can you see my screen?
Yes, we can.
Okay. So hi, my name is Krystal Maughan. I'm a current rising third-year PhD student at the University of Vermont, advised by Jui and Krystal Vincent. Before that, I studied film photography and visual arts and worked in Hollywood. Today, I'm going to give a brief talk on my reinforcement learning open source FEST project, which is titled Integrate Estimate Library into Azure Machine Learning Pipeline. In this project, I worked with my pair Jui and was mentored by Alexi and Cheung. My project was broken up into 4 main phases. The first was onboarding, in which I was tasked with learning Azure. The second phase was building a distributed pipeline to run local jobs on the compute cluster. The third was in designing the input data format and aggregating the data after the estimators from the library, which Jui had worked on, had been run to provide the user with visualization. Finally, the fourth phase involved testing, working on the visualization interface, and documentation for wrapping up the project. The high-level motivation for the project is that in reinforcement learning, there's often an enormous amount of logs for all decisions of reinforcement learning systems. Offline, we need to estimate counterfactual performance of other policies based on these logs and compare them with online performance. In order to do this, we have the Estimators library, which is a core library for algorithms for estimating counterfactual performance of policies, but we need to integrate this with an end-to-end pipeline in a consumable way. And why Azure? Well, there are multiple platforms to build pipelines, but we decided to use Azure ML because it allows you to run arbitrary single or multi-node jobs using Python. And our estimator library is written in Python. So when running multiple node jobs, there are multiple frameworks. And since Azure ML supports MPI jobs, and MPI is the standard framework for distributed processing, we chose to use that. But why this project? And why should we as users care? Well, that's a great question. So let's start with the expectations of the user. My user wants to run SNPs and MLE estimator on different input files, aggregate the results, and visualize them. So they start with a local notebook where they can locally load the log decisions and policies configurations and the input files 01.csv and 02.csv, respectively. They then want to send their job to the compute cluster, which will run distributed and parallelized jobs of estimators from the estimator library as specified by the policy and the configuration set locally on different compute nodes for the different files. Finally, this output will be aggregated into two files, 01.csv.aggregated and 02.csv.aggregated. The user will be able to download these files and see the resulting visualization of the aggregated plot in an interface which we have designed. Our system can not only do this, but we can do this at scale. So I use the example of the two files for simplicity, but the end-to-end distributed pipeline is scalable and should enable a user with multiple files to run distributed jobs on the compute cluster and receive output over multiple policies, as well as the expected visualization from running these jobs. I'd like to talk about two of my personal milestones. My first personal milestone was being able to run a single node and a distributed job with data parallelism on the compute cluster. By June, I had made my first pull request and successfully been able to navigate the compute cluster space and run both single nodes and jobs with data parallelism on the compute cluster. So this is my first major milestone. My second major milestone was completing the end-to-end process for input files and creating the visualization for the distributed runs. So some things are better to demo. So it's everyone's favorite time, demo time. I plan to do this live, but sometimes compute cluster jobs take a little bit longer than we would want. So I've created a demo notebook, which I will put up in the data science repo, and I'll show where my job is run and what the output looks like in real time. So user will start by configuring their compute cluster locally, as we can see here, by defining the workspace and region on our compute cluster. So from here, we see our compute cluster, our lowest CFE cluster, and set our compute target. If there's not one that exists, one will be created. We then define our source directory, which is called script run. And we have a script, which is setup mpi.py. The logic gives us a distributed parallelized setup so that the number of nodes is obtained and the node index is obtained so that we can split the number of files into the nodes, in this case 2, and run the estimator according to the estimators defined in our config and our aggregation number, which is 5,000. Next, we have our blob store compute, and we set that and make sure that our conda dependencies are installed. So here we can see that our VW estimators library is a dependency that needs to be installed on each node for files to be processed correctly. And next, we'll define our script and arguments and the node count. So here we see the node count is 2. And next, we'll build and submit the experiment. So I'm going to run the job live here, even though this is pre-recorded. So please bear with me a bit. Here's the Azure portal. And as you can see, I've previously run a job. So now the job is running, but it still needs to build the Docker image first and install the dependencies on each node, as well as the appropriate data for each node. So fortunately for us, this run hasn't taken too long. So we can see all of our logged files and see that the run was successful. And I ran a number of jobs when I recorded this, and Azure does some neat caching to optimize the time we wait once we started running jobs in succession. So it shouldn't be too long. We just need a little bit of patience. Okay, so refresh again. And we see that the job is finalizing. And then it will be done. Okay, so now back to our notebook. And now I can download the files and visualize the output. So here we see the results of the estimator functions run according to the config, which were aggregated in the folder outputs as shown. So that is, we can see the results of running the estimators function from our CSV files as aggregated via our estimate function, which is processed via our two nodes on a distributed parallelized job. We download our output aggregated files and we plot this graph. Which runs the estimator function on the files in sequence using the coin IPS, random IPS, and baseline 1 IPS as we defined in our config. So for those wondering, coin IPS is a specific column where IPS is run, which represents the probabilities for learning using a coin betting algorithm. So now I'm going to go back to... So here's a list of all my completed goals this summer. It involves my first pull request to when I completed my test coverage, enabled distributed runs, and worked on iteration for plotting the aggregated data from the estimators library, which Jui had worked on this summer. So this is not to say that there were not challenges. Some of my personal challenges were skilling up, and for this pairing was quite useful. We also had an international team, so we had to plan for that in our syncs, which are once a week, and at least twice for individual mentors. On top of that, I was also pursuing a full-time internship for which I received a return and full-time offer last week. And my intern presentation for that is also this week. I also worked on 2 research papers, one of which is under submission and the other which is due this Friday. And finally, I'm working with a pair at Google Brain on an outreach program for ICLR 2022 to encourage broader participation in research. So balancing all of these activities and mental health was crucial for me. So what's next in terms of future work? Well, I'd like to add confidence intervals as well as expand the number of options supported by our config. I'd also like to explore other log formats such as CCB, Slates, and CA, and improve code stability and error reporting. So it's been a really great summer, and I worked with a really patient, helpful team. The whole process was just really enjoyable for me. So thank you so much, Alexi, Cheung, and Jui, for a great summer.
Thanks a lot for your work, Krystal. It seems quite impressive. Thank you.
Thank you.
Thank you, Krystal. Our last student today is Jui. Talk about integrating the Estimator library on AML.
Thank you, Jack. Is my screen visible?
Yes, we can see it.
Okay, so hello everyone. I'm Jui Pradhan. Oh, I think I've not switched on my camera. Sorry. Yes, so hello everyone. I'm Jui Pradhan, and as a part of PLOS 2021, I've been working on the project titled Integrate Estimator Library into AML Pipeline. My mentors are Alexi and Cheung, who provided valuable feedback and direction for this project, for which I'm truly grateful for. So before getting into the details of the project, let me introduce myself real quick. I'm a rising junior at BITS Pilani, India, pursuing MSc Economics and PE Computer Science. My interests involve working on AI research projects and contributing to impactful open source projects. And a fun fact about me is that I love to paint. So let me come to what problem we are trying to solve. Let me take a typical user's visit as an example. The user comes to a website, inputs some query. Next, the website will recommend a list of items to the user. The user's engagement with the recommended items is then observed. We observe information such as did they click, how long did they read, what was their dwell time, etc. This is called feedback. So the goal of the recommender is to maximize the user engagement. However, it is worth noting that we receive feedback only for the presented action, and the feedback for other predictions are typically unknown. So typically, we want to measure the expected reward for a new policy pi using the log data from a different known policy mu. One way to measure the reward is to deploy the new policy pi online and capture data to determine how the new policy is going to perform. However, such online evaluation can be very costly for two reasons. First, it exposes the user to an untested experimental policy, and it does not scale to evaluating multiple target policies. Essentially, we are trying to solve the counterfactual evaluation problem, also called off-policy evaluation. So this is where the estimator library comes in. The estimator library is a collection of estimators to evaluate do off-policy evaluation. And my work this summer involves improving the already existing prototype of the estimator library. There are some known challenges and problems with the previous prototype of the estimator library. First and primary problem being that it lacked a clear structure. So for anyone who was new and wanted to add new estimators to the library, it was difficult for them to find where and what needs to be implemented. Secondly, the package was hard to install and consume. So before we could not do something as simple as pip install VW estimators, but now it's possible. And lastly, there were insufficient tests. So coming to project goals and roadmap, I started with designing a clear structure for the package, then worked on interfaces for each problem type, then moved to adding tests and CI improvements, followed by adding new estimators, and finally releasing the estimator library to PyPI. So this was originally how the estimator library looked like. You can see that it does not have a clear structure. So we segregated the estimators based on the problem type. The image on the right shows the package structure of the improved prototype. Moving to the work on my project, I designed and added new interfaces for each problem type, along with updating existing estimators and scripts to use new interfaces. Next, I added an interface and an estimator for CCB, which is also short for conditional contextual bandits. I also worked on tests for each problem type in separate files, test bandits, test states, test CCP. We worked on unit tests and end-to-end simulation-based tests. Lastly, I added CI improvements like extending support for Python version 3.9 and generating test coverage. I also improved error handling and worked on improving code quality by dependency refactoring and doing an end-to-end code cleanup for adding examples. So we were able to achieve one major project milestone. That was we were able to release the estimators library on July 9th as VW estimators for everyone to use. And now the VW estimators library can be consumed not only by the AML pipeline, but also by users. It can be easily installed by doing something like pip3 install VW estimators. So for the code demo, I would be walking you through the screenshots of the code and the output, just so that we're respectful of the time. I would like to highlight the key differences between the earlier usage of the estimator library compared to the improved version. Particularly in this slide, I will be highlighting the changes in code to use MLE and IPS from the previous prototype of the estimator library. So as you can see on the left is the code for MLE, and this is the output. Now this is the code for IPS, and this is the output. Note that in this case, the getEstimate method for MLE and IPS takes different parameters. Hence, the functions are fundamentally different for both MLE and IPS. So in this slide, I would be using the improved prototype to do the same thing. So again, this is the code for MLE. This is the output. Code for IPS, followed by the output. Notice here that we change only the class object and use the same function, estimate, for both MLE and IPS. So now let me answer the question, what difference is this making? Consider that we want to use different estimators over the same data. For example, I want to run MLE and IPS over the same data. In the old prototype, as you can see, due to the difference in number and type of parameters, we need to implement two functions, that is estimate_MLE and estimate_IPS. This is the output for the code. And in contrast to that, in the new prototype, we can reuse the same function instead of having to define a new function for a new estimator each time. This is again the output for the code snippet. And this is a direct result of my work on interfaces and code quality improvements. We have achieved two positive impacts by making changes. First being it improves code readability and generates, it greatly improves code readability. Secondly, the user can now easily write code that runs over multiple estimators for the same data. So essentially, we can have a for loop and iterate over the estimators and reuse the same function each time. So let me briefly walk you through the high-level process of adding a new estimator to the library. Step 1 is to identify the problem type and find the estimator to use. You can do that by looking at the data type of plog, reward, and pthread. Step 2 is to know what each interface is implementing. The interface for each problem type is implementing two classes, estimator and interval, each having two functions, addExample and get. So addExample takes in 3 arguments, that is plog, reward, and pthread, each having a different data type, and the get method returns the estimator value. For the class interval, addExample again takes in 3 arguments, plog, reward, and pthread with different data types. The get method here also takes an argument alpha, which is a float, and returns the confidence interval as a list of 2 float. So let me take an example of adding a new estimator, starting with a commonly used estimator. Let me walk you through the steps for adding IPS. Since plog and pthread are floats, plog, reward, and pthread are floats, we would use the Bandits interface. Next, we would implement the 2 functions in the estimator class, that is addExample and get. The step 3 is adding tests. As you can see, these tests are divided into 3 major modules, test bandits, test slates, and test CCB. For IPS, as identified in step 1, we would find the test in test bandits. And adding tests is now fairly simple. So you just have to add your estimator and the expected value as a tuple here. And lastly, step 4 is to make a pull request against the estimator library, and your code will be merged. Coming to future plans, there was originally some work done as a part of FLOSS 2020, which has several new Bandits estimator implementations, which can be adapted to use the new interface. And we are also working on separating cats. So originally, cats was implemented not as a separate problem, but as an adapter to the Bandits problem. But in the future, we could work on separating it. And lastly, there is always a scope for code improvements. So my key learnings and takeaways. My journey so far has really been fun. And previously, I've worked on projects focusing on NLP and information retrieval, but this was my first experience and exposure to RL. And I'm really, truly grateful for having gotten this opportunity. And I came into this project with some experience in Python, and I really learned how to work in a more professional quality setting. So my key takeaways from this project are learning to implement interfaces in Python and grasping few Azure fundamentals. I also learned how to use GitHub Actions while I worked on CI improvements. And finally, I learned how to release a package to PyPI. Moreover, I've been reading research papers on off-policy evaluation, slates, etc., to get a more in-depth understanding of what I've been working on. Lastly, I would really like to thank Alexi and Cheung and Krystal for all the fun and productive meets. Thank you. Thanks for listening. And if you have any questions or want to connect, feel free to connect on LinkedIn. And thank you so much. I would like to take questions.
All right. Thanks, Jui. It's really great to see like the estimator libraries finally getting to shape where it's more generally usable. That was like a very problematic area for us. We recognized it could use a lot of love, and it seems that it happened this summer. Thanks a lot for the contribution and the work.
I agree. It's so exciting to see that. Awesome stuff.
Yeah. So I think that concludes today. Next week we'll have the other half of the students present their work, and thanks everyone for being here today.